Alright, so we begin with chapter 5. In this part we will have section 5.1 and 5.2. In 5.1 we introduce three concepts. First is the gradient, then is the potential, and the Laplace concept of Laplacian. The first and the third one are mathematical operator for partial differential. It's a partial differential operation in space. So it's a spatial differential operator, which are gradient and Laplacian. Potential is an imaginary physical parameter that it can be configured based on spatial differentiation of actual physical parameters. So in this section, we will discuss the three concepts. So in electromagnetics, we already discussed Maxwell equation and its application in chapter 2, 3, and 4. And we also derived the equations, the so-called plane wave equations for propagating electromagnetic waves. And in this chapter, we will try to establish some basic ideas for transmission lines, and they also involve Maxwell equation. And in particular, we will introduce two potential. One is the so-called electrical scalar potential. The other name for the electrical scalar potential, which you are supposed to be more acquainted with, is voltage. Voltage is in fact the so-called electrical scalar potential. Is voltage a real physical parameter? No, it's not. 所以电压不是真实的物理参数哦。电压其实是我们怎样？我们所想象出来的，也不能说想象出来了，我们所创造出来的一个比较容易理解的物理参数。怎么说？老师不会吧？我从高中就开始学电学的时候就开始讲电压，你现在跟我讲电压不是真的。的确不是它其实是所谓的电位能、电存量位能，而电存量位能其实是建立在所谓的电场，电场沿着特定方向所改变，电场沿着特定方向变动，它的电位，我就是说它的电位能会有所变化。所以这一个变化的电位能的那个变化的电位呢，我们就称之为电压。所以真实的物理参数其实是电场 （electrical field）， 这是我们在 Maxwell equation 里头可以直接看到的。但有的时候，也不能说有的时候，其实大部分的时候，电压比较好用就像各位在学电学的时候用的都是电压所以电压其实是 electrical potential， 它不是真实的物理量，它是借由电场来去创造出来的但相对于电压是什么？电流嘛但电流是真实的物理量嘛electrical current is an actual physical parameter. And on top of the electrical scalar potential, another potential that we will introduce in this chapter is the so-called magnetic vector potential. So as the name suggests, you know that the magnetic vector potential is related to magnetic field, and it's in the form of vector. In contrast to the voltage, which is a scalar potential. The magnetic vector potential is a vector, alright, as the name suggests. Alright, and the very last entry says that we are preparing for the discussion for transmission line. Alright, so we will first introduce the electrical scalar potential and function, and then we will try to describe the transmission line theory, which is in contrast to the so-called lump circuit theory, which are based on capacitance, conductance, and inductance. Alright, and well, in the later part of this chapter, we will discuss about the electrical circuit as well as magnetic circuit, and they are all related to electromechanics, 电动力学. Alright, in section 5.1, we will try to introduce the idea of vector potential. We will introduce the spatial differentiation operator, that is the gradient T2, gradient T2, and so that we can express field in terms of potential, and including both scalar potential and vector potential. Then we will introduce another spatial derivative, that is the Laplacian operator. And so that we can express the Maxwell equation in terms of scalar potential and vector potential. Then we will describe the Helmholtz theory, Lorentz condition and Helmholtz theory, so that we can write up the second order partial differential equation pertinent to the electromagnetic wave using vector potential and scalar potential. Alright, and还记得那个什么吗？ Maxwell equation 吗？我们写那个 differential form 的 Maxwell equation。所以第一条什么？法拉第定律嘛，这个是什么 ？Kerr 旋度，Kerr 旋度。所以第一条法拉第定律告诉我们什么？电场的旋度。什么叫电场的旋度？电场在空间中的变化。所以你看到 del 是什么？这个倒三角是什么 ？del operator 它是空间的偏微分运算子。所以你看到倒三角，我们就知道要把这个物理量在空间中去做检查。而检查的方式有很多种，有 Kerr， 有等一下看到的 divergence， 还有我们今天要介绍的 gradient， 至少有这三种。但接下来你看到的Laplacian也是，是空间的偏微分。所以第一个法拉定律告诉我们什么？电场在空间的变化跟什么有关？跟磁动量密度在时间上面的变动率的负值有关系。第二条呢，称之为什么？它没电路定律，所以磁场强度的空间变化，磁场强度的 Kerr 等于那一个位置的电流密度以及那个位置的电通量密度的时间变化。下一个呢？ OK， 这是什么 ？Divergence of D。Divergence 是另外一个空间偏微分子所以称之为散度 divergence。Kerr 的话称之为旋度，它们两个差在哪里？旋度的话，我喜欢它叫做 lateral derivative， 横向的变化。也就是说，电场只要往前面这个方向，那么你在做 Kerr operation 的时候，其实检查这一个电场，这里的电场跟它边刷尾几波它的那个电场有没有差异？假如不一样的话，那它就有 Kerr。 往左往右往上往下，这是 correlation。但在 divergence operation 的时候呢，你的电场或者是电通量密度是这个方向，而它检查的那个空间变化的方式呢，是沿着这个方向。所以我习惯叫它叫 longitudinal derivative， 顺着这个场的方向去检查它场的数值有没有变动，场的数值、场的方向有没有变动啊？因为毕竟这个场都是向量，所以这条叫做高斯 law of electrical field， 高斯电场定律。所以，假如在空间中某一个点，它的电通量密度或者说它的电场 divergence 不等于0的话，表示什么？那个地方有电荷，电荷。那第4条呢 ，divergence of B equals to 0。任何地方的磁场、磁通量密度的 divergence 都等于0。为什么？因为磁场必定要绕一圈回来，所以我们没有所谓单独存在的磁核。只要你能够证明这个东西不等于0，那么你就可以有所谓的 magnetic charge。magnetic charge。那当然了，真实世界里头没有 magnetic charge， 至少到目前为止没有看到。所以这一组式子里头，你看到了什么？ In Maxwell equation in differential form, we see the left hand side of the all four equation are spatial derivative of electric and magnetic field. How about the right hand side? The right hand side, the Faraday's law and the Ampere's potential law suggest the existence of electric and magnetic field are related to the time derivative of electric magnetic field and electrical field. All right? So this is the principal mechanism for the generation of electromagnetic wave. So they are related to temporal dependence, time derivative. Another important thing is this thing, J and rho. J is electrical current density, rho is electrical charge density. So they are the sources for electromagnetic field. The presence of electrical current density directly produces magnetic field. And the presence of electrical charge density directly produces electrical field. So we can say that we know in chapter 3 we already discussed that the direct product for electrical charge is electrical field. The direct product of direct electrical current is magnetic field. Correct? And in the application of electromagnetic study, in general, we would like to know the electrical field distribution, not only in the region of sources, including current sources and charge sources. We would like to know what is the electric and magnetic field distribution, EM field variation due to the presence of electric and magnetic source at a remote site. All right? So we know that in the application of wireless communication, the transmitter produces electromagnetic wave using alternating electrical current. And it produces electromagnetic wave. And we propagate to a remote site, a distance away from the sources, away from the antenna. And it will produce electrical and magnetic field variation in this remote site. And it seems intuitive that once we know the source distribution and its spatial its time variation, we are supposed to know the field because this is a propagating phenomenon. Because the wave will propagate, will go further and further. However, the solution can be very, the derivation of the solution can be very difficult in general. So, we devised another technique, we devised an alternative approach, that is to calculate the so-called magnetic vector potential first. Then, using the magnetic vector potential, we can calculate the electrical and magnetic field distribution in the far away side. So this is kind of a two-step process. However, it's much easier. First, we will demonstrate this process, this approach, in the later part of this course. All right? And before we proceed for the discussion of this approach, let me first describe two vector identity. On the top of this slide, we have one vector identity. Notice that the spatial operator has some priority. You need to perform curl operation first. The priority of curl operation is higher than dot product. So we write so that this vector identity read as the divergence of the curl vector A. It must equals to 0. This is so-called the vector all right, another one is this. The curl of the gradient of any the curl of the divergence of any scalar must equals to 0. So in this section, we will introduce these two vector identities. So based on the first vector identity and the Gauss's law for magnetic field. If you compare this Maxwell equation with this vector identity, you can see what is the conclusion? What is your derivation? You can say that the vector B, the magnetic vector potential, the magnetic flux density. The magnetic flux density can be expressed as the curl of another vector. So this is equation part 1. The magnetic flux density B can be expressed as the curl of magnetic vector potential A. So A is namely the magnetic vector potential. By taking the curl of A, we shall plot the magnetic flux density. 所以这里头我们把 A 定义为所谓的磁向量位能。那你不知道 A 长怎么样？到目前为止不知道 A 长怎么样。那我们可以知道的是。有一个向量 A， 你只要对它取旋度，那么它的结果会等于磁通量密度 B， 因为 B 的散度一定为零，而这个 vector identity 告诉你，任何的，假如有一个向量的散度为零，那么这个散度可以被表示成是不是这个散度。这个向量可以被表示成是某个向量的旋度啊。OK， 那这是一件事情。接下来我们看另外一件事情。In the first Maxwell equation, the Faraday's law, we know that the curl of E equals to the minus of the time derivative of B. And if we substitute B with curl of A, we end up with curl of E plus the time derivative of curl of A equals to 0. Correct? This is the equation we have here. Another thing is we can get the result of equation 5.2 and collect the two terms into one term. That is the curl of E plus del A over del T equals to 0. You're supposed to ask the question, is that a legal process? Because we interchange two differential operations, the order of the two differential operations, right? We first taking the curl of A, taking the special derivative. Next, we take the time derivative of this result, the curl of A. So in this equation, we first do the special derivative, then do the temporal derivative. Temporal derivative is time. However, in this equation, the order is in the trench. We first take in the time derivative of A, then we take in the special derivative, which is a curl operation. Is that legal? Of course, it's legal. Why? Because the world we are living in right now is three-dimensional or four-dimensional, or 3 plus 1. It's three-dimensional in space and one-dimensional in time. And time, the dimension of time and dimension of space are independent. At least in the world that we experience. Of course, if you are in the world of, say, the beginning of Big Bang, or in the world that is going to go into a black hole, so for those extreme circumstances, the time and space may couple together. Otherwise, for ordinary conditions, the time and space are independent. So the differential operation of time and space can be interchanged, right? Okay. So we can have equation 5.2, that is the curl of something. Is this a vector or a scalar? Well, it's a vector. Otherwise, you cannot perform the curl operation. The curl of a vector equals to 0. Then we can use this vector identity. If you have something that is the curl of this thing, of this vector equals to 0, then the vector can be expressed as a gradient. All right, so we use this vector identity that for any scalar, if you take the gradient first, and then taking the curl product of this, the curl of this, it always goes to 0. All right. So, of course, we will discuss a little bit about gradient operation. However, gradient operation can only be performed on scalar. 梯度是对纯量去做空间的一个操作，而梯度本身是纯量还是向量？向量哦。把一个纯量对它做空间的微分，做空间的梯度微分，它的结果会是一个向量。这样的向量你才能够拿来做curl operation。所以，假如某向量的旋度为0，那么这个向量可以被表示为是某个纯量梯度。所以 curl of a vector equals to 0, then the vector can be expressed as the gradient of a scalar. And this is true for any scalar. It's true for any scalar. All right? So what is gradient? The gradient of a scalar, say phi, denoted as scale phi, is defined in such a manner that the increment in phi from a point for neighboring point Q is given by this equation. So you need to understand this equation. So this is gradient. This is amount of trend. This is the gradient of a scalar per meter. It can be a physical parameter. For example, the height of a hill, the height of a mountain. So suppose this is a map, and the darker area is the region of higher altitude. And the lighter region are regions of lower altitude. 所以高度比较大的，就是高度比较小。而这个箭头呢，事实上就是你能够理解坡度，就是高度的变化，高度的变化率，我们称之为gradient，可以，它其实就是一个gradient。所以这些箭头告诉你什么？告诉你高度的变化率是朝这个方向，所以这个地方是高度最高的。高度比较小，而这个图告诉你什么？它的高度是比较均匀的，由右往左升高。所以d phi 是变化量，第一条是变化量，比如高度的变化量。第二 phi 是变化率，而 dl 呢，还记得吧？这个叫什么 ？differential length， 它是一小段长度。而这一小段长度是有方向的，所以一小段长度的方向跟变化率的内积是以 dot product 的形式去计算。假如它不等于0的话，就表示它有变化量。例如说，这边这个图的话，你有往左走，你的高度不变化。有变化量，有右往左，有左往右走，有没有变化？它负的变化量，高度越来越低。但是，只要你的走的方向是由下往上走，或由上往下走，它有 dl 是往上或往下，它有gradient of phi， 也就是它的梯度，但是。你只要往上或往下走的时候，你会发现你走的方向跟这些蓝色箭头是正交的，也就是说它是正交的，所以内积为0。所以注意你在取那个计算变化量的时候，你的 gradient 跟你的变化方向必须要有一定程度的平行量。假如你是完全正交的话，那你沿着这个图往上或往下走是没有变化的，no change in the altitude, no change in the magnitude. All right, so here's some problem. I guess I will probably stop here. So the gradient operator del phi is other differential equation in x, y, and z direction. So it's a vector. Del phi is in the form of a vector. Dl is a vector. However, the dot product of the two becomes a scalar. All right. So we will continue our discussion on Friday about gradient. All right. So any questions so far? 好吧，我尽量试着，没有说一定要全英文的。OK， 好，但是系主任我不跟你讲。OK 好，那个我们今天到这边了需要授权码的来找我。OK， 但一般电机系的同学应该是可以直接在选课系统上直接选的